We are asked here to look at a truss that's made up of two members, CD and BD, which are pinned together at joint D. There's a vertical downward load P acting at joint D. In addition to the mechanical load, we also have known information that member 1 is going to be changing in temperature by an amount of delta T, where member 2 remains unchanged. We're asked to find two things. One, what are the axial stresses in members 1 and 2? And 2, what are the horizontal and vertical components of displacement of joint D? Okay, we're going to start out with a little bit of trig first. I'm going to define this angle between the two members as phi. And from the figure here, we can see that since one has a length of L, then phi is the inverse sine of H over L. In order to use our truss compatibility equation, we're going to need to correctly define our angles for members 1 and 2. So we go back to the base where the member is attached to ground. We strike out an x-axis and we measure counterclockwise around to the member. So theta 1 in this case is going to be 360 degrees, subtract away phi, whatever that ends up being. So we now know theta 1. Theta 2, strike out an x-axis, measure counterclockwise from there, and we see that theta 2 is equal to a 0. We'll also note that the length of 2 is going to be the square root of L squared minus H squared. We'll use that later on. So these are the two angles that we're going to need. So we're going to go through our 4 steps in one way or another. The first step is to do equilibrium. What I'm going to do is draw a free body diagram of pin D. So I'm going to have the member 2 load F1, member 1 load F1, angle of phi between them, and then there's a load of P acting like this. I'm going to make X to the right and Y up. My equilibrium equations are summation of forces X is a minus F2 minus an F1 cosine of phi equal to a 0. And summation of forces in Y gives us F1 sine phi minus P is equal to a 0. So from here we can see that the load F1 is going to be equal to P divided by sine phi. From here we can see that F2 is going to be equal to minus F1 cosine of phi, so that's going to be, in the end, I didn't give myself much space here, so that's going to be equal to a minus P times cotangent of phi. So this is going to be F1, and this is F2. I'm sorry, this is F2, isn't it? So that's F2, this is F1. I'll get it straight. From this, we can get our stresses, sigma 1, that's going to be F1 divided by A1. So that's going to be P divided by A sine phi. Both areas are the same. Sigma 2 is F2 over A2, so that's going to be equal to a minus P over A cotangent phi. So these are the stresses that are carried by members 1 and 2. We will have our force elongation equations. Where we recall here that 1 has both mechanical loads and thermal loads. So with E1 is equal to F1, length 1, divided by E1 A1, plus alpha delta T times L1. So F1 is going to be equal to, I'll just write that as F1 for right now, F1 times L. E is equal to E1 is equal to 2E, so this is 2E over A plus alpha delta T times L. The elongation for 2, that's going to be F2, L2, E2, A2. So that's going to be F2, that boxed in equation up there. L2 is L squared minus H squared divided by EA. So this is going to be equation 1 and 2. And so now we have our truss compatibility. We're focusing there on joint D. So we know that E1, 1 is connected to D, so E1 is going to be equal to UD cosine of theta 1 plus V sub D sine theta 1, and E2 is going to be equal to UD cosine theta 2 plus V sub D sine theta 2. Theta 2 is a 0, so sine becomes a 0, cosine becomes a 1, and here we see that the elongation of 2 is nothing other than the horizontal displacement there for D. So at the solve phase, we can find therefore that the horizontal component of displacement of D is going to be equal to E2. E2 is going to be F2. F2 is a minus P cotangent phi. That's F2 times square root of L squared minus H squared divided by EA, like that. And we know that V sub D is going to be equal to E1 minus UD, where E1 we saw was equal to F1, and F1 was P over sine phi. That's P over sine phi. L over 2 EA plus alpha delta TL minus U sub D, so that's going to be a minus, and a minus makes that a plus, P cotangent phi square root of L squared minus H squared divided by EA. So these are our components of displacement, UD and VD. In summary, what we did was we began a problem by looking at equilibrium, a first step for just about everything in this course. I chose to do an equilibrium of joint D, from which I was able to solve for F1 and F2. The loads carried by members 1 and 2, so right away from there I was able to get the stress. Then, in order to find the elongation, I began writing the relationship that exists between elongation and the loads. Those are two compatibility equations, 1 and 2. Force elongation equations 1 and 2. And then I used my truss compatibility equations that we derived there in the lecture book to relate the elongations back to the displacements. So this is, again, an example here where elongation and displacements are not the same thing. Elongations are only part of the overall displacement. So we're able to use those two equations. So it was really the four-step plan, but in this case we were able to determine the stresses right from the word go. We just carried through with the rest of it in order to pull out the deformations.